This video reviews two key ideas for understanding the quality of a prediction of a random variable y based on a random vector x. Suppose that we want to predict y using x. There are many different ways that we could think about doing this, and there are many different ways that we could think about evaluating the quality of our prediction. But a particularly common way of measuring the quality of a prediction is to consider mean squared error. Suppose that phi of x is our predictor of y based on x. Then we may look for a choice of predictor that does a good job on average of predicting y, in the sense of being close to y in Euclidean distance. This is effectively what mean squared error is. It's the average squared distance from y, the truth, to the prediction, phi of x. If we want to choose the best possible predictor for predicting y in terms of minimizing mean squared error, then we're looking for the function phi that minimizes this quantity over all possible functions phi. As you probably learned in your lectures on introductory regression earlier in the academic year, the solution to this problem, in other words, the function that minimizes mean squared error, is the conditional mean of y given x. We'll prove this on the next slide. Another way of trying to predict y using x is to restrict our attention to certain kinds of functions of x. One particularly common choice is the class of linear functions. So suppose that rather than considering all possible predictors phi, we restricted our attention to functions of the form x prime theta, where theta is a vector of parameters. This is the problem of trying to determine the best linear predictor. If again, we set about to choose the linear predictor that minimizes mean squared error, we obtain what's called the minimum mean squared error linear predictor. And as I hope you recall, this problem is precisely population least squares linear regression. Now we'll prove that the conditional mean of y given x is the minimum mean squared error predictor of y using x. We'll do this in 3 steps. In the first step, we'll use the oldest trick in the book. If you want to make a certain quantity appear in an expression, simply add it and subtract it. Here we'll add and subtract mu of x. When we do so, and we regroup terms as follows, expanding the quadratic inside the expectation gives us 3 terms. The first is the expected value of y minus mu of x squared. The second is a somewhat complicated expression that we'll come back to in a moment. And the third is the expected value of phi of x minus mu of x quantity squared. Now let's take a closer look at this second term. Another useful trick when you don't know how to calculate an expectation is to see if there's some way of simplifying it by using iterated expectations. That's what we'll do here. So we'll apply the law of iterated expectations, conditioning on x. Now the reason why this is a reasonable thing to try is because we notice that one of the factors in this expression, namely phi of x minus mu of x, is just a function of x. So the inner conditional expectation with respect to x is such that we can pull this term in front, leaving the following. Now, take a look at the second factor inside of these parentheses. We have the expected value of y given x minus mu of x. But remember that at the top of this proof, we actually defined mu of x to be the conditional expectation of y given x. That's just shorthand. So what we find is that the second factor is 0, and therefore the entire expression is 0. This means that of the 3 terms we started out with by expanding the quadratic, we can ignore the middle one. Finally, we combine steps 1 and 2 by taking a look at the remaining terms in the expression now that we've eliminated the middle term, which is 0. Let's look at the first one. The expected value of y minus mu of x squared is a constant with respect to phi. This does not in any way include phi, so there's no way that we can affect it by changing which predictor, phi, we substitute into the objective function. So this means we can completely ignore this term as far as the optimization is concerned. Now, let's take a look at the second term. This is the expected value of something squared. If I square something, I can't get a negative result, so this expectation must be non-negative. However, notice that we can make it exactly equal to 0 by choosing phi cleverly. Phi could be any function we want, so why just can't we make it the same thing as mu? Indeed, we can, and if we do this, then the term will be exactly 0. The expectation of 0 is just 0. This shows that if we set our predictor, phi, equal to the conditional mean of y given x, we make the second term 0. And because the first term is a constant with respect to phi, we have found the predictor that minimizes the mean squared error, and it's the conditional mean. And how do we know this? Well, that's because given that the second term can't be negative, there's no way that we can improve upon making it 0, no matter what other function we might care to try to substitute for phi. And now we quickly review a proof with which you should be familiar, namely that OLS provides the minimum mean squared error linear predictor. Writing down the familiar objective function and expanding, we obtain the following, noting that the expected value of y squared is a constant, so is 2 times the expected value of y x prime, and so is the expected value of x x prime. Each of these are constants with respect to our optimization problem, which is over theta. Recall 2 important facts from matrix differentiation. First, if A is a column vector and Z is a column vector of variables, then the vector of partial derivatives of A transpose Z with respect to Z is A. And if A is a square matrix, such that Z prime A, Z is a quadratic form in Z, then the partial derivative of this quadratic form with respect to Z is A plus A prime quantity multiplied by Z. And indeed, because it's traditional to write a quadratic form using a symmetric matrix, in which case A is equal to A transpose, the case where A is symmetric gives us 2A times Z. Applying these to the objective function from above, we obtain the following first order condition, and provided that the matrix expected value of x, x prime is invertible, we obtain the familiar OLS expression in the population.